If you follow scaling laws in machine learning, you know the conventional wisdom, right? Compute is king.
Oh, absolutely. That's the mantra.
Yeah, we've all been sort of conditioned to believe that when it comes to large language models, just throwing more parameters and more GPUs at a problem is, the ultimate path to higher performance.
Right. Just scale it up and it'll figure it out.
Exactly. But what if I told you that a 7 billion parameter language model could completely outperform a 671 billion parameter giant, specifically in formal theorem proving?
Wow, that's a massive difference in scale.
It is. And what if it pulled this off not through some massive leap in hardware or, I don't know, a radically new attention mechanism, but simply by learning how to properly guide its own self-play?
It sounds like a paradox, especially in an era where massive scale usually just dominates the leaderboards.
Yeah, totally.
But in the highly rigorous domain of formal mathematical reasoning, brute force scale actually hits a very hard ceiling. I mean, when you require absolute logical precision, simply scaling up the data and the parameters, it doesn't automatically translate to better problem solving.
Makes sense. It's not just about predicting the next likely word anymore.
Exactly. And that ceiling is exactly the bottleneck we need to analyze today.
Right, and that's the core of what we're digging into. We're looking at a fascinating 2026 paper from researchers at Stanford University titled Scaling Self-Play with Self-Guidance, or SGS.
Really great paper.
Yeah, it's incredible. The mission for this deep dive is to unpack the exact mathematical and architectural mechanisms that allow SGS to overcome the notorious learning plateaus that plague LLM self-play algorithms.
Plateaus that are incredibly frustrating, by the way.
Oh, yeah. If you've ever tried building or tuning these systems, you know exactly what plateaus I'm talking about. Okay, let's unpack this. It's like a teacher, which would be our conjecturer, right? Realizing they're only being evaluated on whether their student is challenged. Instead of creating useful, incremental, stepping stone math problems that actually build the student's foundation, the teacher just starts handing the student heavily convoluted, unreadable, busy work.
Just making it impossible for no reason.
Exactly. It's incredibly hard, sure, but it doesn't help the student actually learn the target material.
That is exactly what happens mathematically. And to really appreciate the architecture the Stanford team built, we have to establish the exact mechanics of the baseline they are improving upon.
Okay, let's set that baseline for the listener.
So as you likely know, asymmetric self-play is a framework where we instantiate two distinct roles within the system. You've got a conjecturer that proposes new mathematical problems and a solver that attempts to generate proofs for them.
Two agents basically playing a game.
Exactly. And in a formal mathematics environment, like Lean 4, for example, the system is beautiful because the compiler acts as a perfect ground truth reward function.
Right, there's no hallucination allowed.
None. If the proof compiles, it is logically correct. There's no ambiguity at all.
So theoretically, that setup should be a perpetual motion machine for artificial intelligence. Like the conjecturer probes the latent space to find the exact edge of the solver's current capability, right?
Right, pushing the boundary.
It generates a problem just past that frontier. The solver runs its policy gradient updates to learn how to solve it, and then the cycle repeats. You should get unbounded learning.
Unbounded in principle, yes, but wildly unstable in practice.
Really? Why is that?
Well, when you try to scale this process, and I mean really scale it with massive amounts of compute over millions of generations, the system inevitably collapses. The learning curve just flatlines.
So it just hits a wall.
It hits a wall hard. And the core bottleneck, the fundamental reason standard asymmetric self-play fails over long training runs, is reward hacking by the conjecturer.
Reward hacking. So the conjecturer starts cheating the game.
Exactly. To understand the Stanford team's solution, we really need to look under the hood at why that degeneracy occurs.
Yeah, break that down for me.
Well, in a standard self-play setup, the conjecturer's reward function is usually tethered entirely to the solver's empirical solve rate. So the optimization objective is designed to favor problems of intermediate difficulty.
Intermediate, meaning not too easy, but not completely impossible.
Right. Think about it. If a problem is too easy, the solve rate approaches 100%, and the reward signal is 0. But if the problem is impossibly hard, the solve rate is 0%, and the reward is also 0.
Right, because a 0% solve rate means the solver generates 0 correct rollouts. And if there are no successful trajectories, there's no positive signal to run a policy gradient update on.
Exactly.
The solver learns absolutely nothing.
Exactly right. So the optimization pressure constantly pushes the conjecture toward this intermediate zone. Now, in a lot of prior literature, researchers stopped their self-play runs relatively early.
Because they just didn't have the compute.
Or they just hit good enough results. But the Stanford researchers wanted to see the asymptotic limits. They ran their baseline for over 6 billion tokens, epoching the target data set like 230 times.
Wow. 6 billion tokens of pure self-play.
Yeah, it's massive. And when you apply optimization pressure for that duration, the conjecturer learns to hack that intermediate solve rate metric. It discovers that the easiest way to hit a 50% solve rate isn't to write a profound theorem.
Oh no, what does it do?
It starts producing artificially complex, structurally bizarre problems.
Hold on, I need to stop you there. This is where the intuition gets tricky for me. Because if the generated problem compiles perfectly in lean 4, meaning it is a mathematically sound theorem, and it sits at that intermediate difficulty sweet spot, why doesn't that extra data provide useful gradients for the solver?
It's a really common misconception.
I mean, math is math, isn't it? A valid, provable theorem should still be a valid training signal, regardless of how, artificial it feels.
This raises an important question, though. What actually constitutes a useful mathematical problem for training a neural network?
Okay, fair point.
The researchers ran a specific ablation study they called No Guide to isolate this exact phenomenon. And they found that without intervention, over 80% of the synthetic problems generated by the conjecturer devolved into what are called disjunctive conclusions.
Disjunctive conclusions, meaning heavily relying on or clauses.
Precisely. The conjecturer starts stringing together totally unrelated mathematical statements with or conditions.
Like prove this thing or this other completely random thing.
Exactly. I might say prove A or prove B or prove C, going all the way down to Z. The paper noted that the length of the problem conclusions actually ballooned to 10 times the average length of the actual target data set.
Oh, I see the trap. It's technically a valid theorem because proving just one of those clauses makes the whole or statement true. But the solver gets completely lost parsing the syntax of the other, 20 irrelevant clauses. So the conjecture is essentially building a maze out of junk logic just to drag the solve rate down to that intermediate sweet spot.
You nailed it. The synthetic problems might be superficially related to the target domain, but they are completely inelegant and structurally useless.
So they don't teach the solver anything valuable.
Nothing at all. Proving them offers zero educational utility for making progress on the actual concise target theorems the system is supposed to master. The conjecturer effectively becomes a troll, prioritizing obfuscation over instruction.
A troll generating math puzzles? I love that.
Which perfectly tees up the core innovation of the paper. Since raw difficulty is clearly an entirely broken proxy for educational utility, the Stanford team realized they needed a mechanism to evaluate the intrinsic quality of the synthetic data itself.
Yes, the quality is paramount.
Enter the self-guided self-play architecture, or SGS. Instead of just two roles, the LLM now splits into three distinct personas. You've got the solver, the conjecturer, and the new addition, the guide. And that guide is the critical regularization term. It acts as an automated defense against degeneracy.
How exactly does it defend the system?
The researchers mathematically formalized this triad by redesigning the reward function for the synthetic problems. Instead of just relying on difficulty, the total reward, which they call rsynth, is calculated as the product of two terms.
Okay, what are they?
It's rsolve multiplied by rguide.
Let's drill down into both of those variables. Starting with rsolve, how are they calculating the difficulty metric in this new architecture?
So rsolve handles the difficulty boundary. For any synthetic problem the conjecturer generates, the system samples multiple proof attempts from the solver. If the empirical solve rate is 0, meaning the problem is strictly out of reach, rsolve is assigned to 0.
Okay, that makes sense. Same as before.
But interestingly, they also implemented a relative cutoff. If the solve rate falls into the top 30% of the current batch, meaning it's trivially easy compared to its peers, rsolve is also forced to 0.
Oh, that's a smart dynamic threshold. It stops the conjecture from just spitting out basic axioms like 1 + 1 = 2 over and over again to rack up points.
Exactly. For everything else that falls into the acceptable middle ground, rsolve is calculated simply as 1 minus the empirical solve rate.
So it still pushes for harder problems.
Right. This scalar actively pushes the conjecture toward the very edge of the solver's capabilities, favoring problems that the solver can only solve, say, 10% of the time rather than 90% of the time.
Okay, so that meticulously handles the difficulty gradient. But as we established with the OR clause mazes, difficulty just isn't enough.
It really isn't.
That's where the second variable, R guide, comes in to save the day, right?
Yeah.
The guide LLM actually looks at the synthetic problem and scores it.
It evaluates how relevant the synthetic problem is to the broader unsolved target problem. It actively penalizes redundant premises.
And crucially, it heavily penalizes complex conclusions.
Yes. The formal calculation for the guide score is uncompromising. It assigns a 0 reward immediately if the conclusion complexity is categorized as high or very high by the LLM.
Immediate 0. That's harsh but necessary.
Very necessary. And if the problem passes that strict simplicity filter, the guide then combines relevance, simplicity, and the lack of redundancy into a single scalar value.
You know, looking at how this is structured, it really highlights a fascinating philosophical point about LLMs.
What's that?
Well, the whole premise of our guide rests on the hypothesis that the language model inherently possesses the latent capability to judge its own work. Like, we are using the model's internal representation of what constitutes an elegant or useful math problem to regularize its own generative output.
It's a profound realization.
Right. It already knows what good math looks like. We just have to prompt it to enforce that standard.
It is a profound realization about the latent knowledge embedded in these models during pre-training. However, tapping into that latent judgment required some very careful engineering.
I can imagine. It's not magic.
No, it's not. The researchers used DeepSeek Prover v27b as the base model for all three roles. Now, because this specific model had undergone heavy reinforcement learning purely optimized for writing Lean 4 proofs, its general instruction following capabilities had severely degraded.
Oh, right, the alignment tax. When you heavily optimize for one highly specific modality, like compiling formal math, the model forgets how to just have a normal conversation or format a JSON output.
Precisely. When they initially prompted the base model to act as the guide and output these specific evaluation metrics, it only produced the correct parsable formatting 54.7% of the time.
Wait, only 54%, which is a total non-starter for an automated large-scale reinforcement learning pipeline.
Exactly.
You absolutely cannot have half of your reward signals throwing syntax errors when you are trying to run millions of generations.
So, to bypass this, the researchers executed a highly targeted supervised fine-tuning, or SFT, intervention.
Oh, nice. What data did they use?
Well, they didn't need to teach the model math. They just needed to teach it formatting. So they used GPT 4.1 Mini to generate 2048 examples of perfectly formatted guide evaluations.
That's a tiny data set.
It is. But fine-tuning the 7 billion parameter DeepSeek model on this tiny specialized data set pushed its formatting compliance from 54% to over 99%.
Wow. It's incredible how efficient that is. It proves that the sophisticated mathematical reasoning and aesthetic judgment required to be the guide were fully native to the 7 billion parameter model.
It was always there.
It literally just needed a slight syntax correction to plug seamlessly into the pipeline.
Exactly. So now we have the fully operational architecture. The solver is actively trying to write Lean 4 proofs. The conjecturer is generating stepping stone problems, and the guide is rigorously keeping the conjecturer honest, blocking the maze-like logic.
But in machine learning, we don't just take an architecture at face value. To prove that every piece of this triad is strictly necessary, we need to look at the ablations.
Absolutely. The ablations are where the real science happens.
I know the researchers ran these tests on a highly curated dataset called D3K.
Yes, D3K consists of 3,323 hard Lean 4 problems. These were auto-formalized primarily from the Numina Math Code dataset.
And these are genuinely tough problems.
Oh, very. The researchers filtered out anything trivial and anything technically unsolvable due to missing formalizations in Lean 4, leaving a pure, highly challenging testbed for the self-play algorithms.
Perfect. Let's talk about the failure modes. What happens if we start pulling pieces out of the SGS triad? For instance, what if we simplify the pipeline and remove the target problem conditioning entirely?
They call that the no-problem conditioning ablation. In this scenario, the conjecturer isn't given a specific unsolved target problem from D3K to look at. It's just prompted generally to generate, quote, a hard math problem.
Does it still generate valid math?
It does. It successfully generates hard problems, and it achieves high solve rate rewards based on the difficulty metric alone.
But does it actually help the system learn?
No. The performance on the actual target distribution flatlines. The synthetic problems are essentially floating in a void. They are totally disconnected from the specific skills and theorems the solver needs to master the D3K dataset.
So it's basically doing random heavy lifting that doesn't apply to the sport it's training for.
Exactly. What's fascinating here is that it empirically proves raw difficulty generation is useless without directional anchoring. The conjecturer must be looking at the goal.
Okay, so the conjecture absolutely has to be conditioned on the target. But what about the reward hacking? What if, instead of building this entire secondary guide model to judge elegance, we just freeze the conjecturer?
Freeze it, like lock its weights.
Yeah. If its weights are static, it can't update its policy to game the reward function. It can never learn to generate those disjunctive nightmares in the first place.
That is a very logical alternative. In fact, it's highly similar to the approach used in systems like AlphaProof, which uses a fixed Gemini model to propose informal problems.
Right.
But the Stanford team's ablation showed that freezing the conjecturer is highly suboptimal for continuous self-play.
Why? If it's generating good problems initially, why does it break down?
Because when the conjecture is static, it generates a fixed, unchanging distribution of synthetic problems. As the solver runs its policy gradient updates, its capability quickly expands to cover that fixed distribution.
Oh, I see. And once the solver masters that static set of problems, the empirical solve rate rockets up to 100%.
Correct. And remember how R-solve is calculated. If the problem is too easy, the reward is 0.
The conjecturer gets 0 reward.
And it is suddenly starved of new synthetic problems that sit in that crucial intermediate difficulty zone. The solver essentially runs out of curriculum, has nothing new to learn from, and the entire system's performance just regresses back to that of a standard baseline reinforcement learning run.
Wow. So it really is an incredibly delicate ecosystem. If the conjecture is frozen, the solver learns everything, hits a ceiling, and starves. If the conjecture runs wild without the guide, it turns into a troll, generating impossible maze-like logic just to keep the solve rates artificially low.
It's a tightrope walk.
Yeah. The guide is the exact mechanism that keeps the entire system dynamically balanced in the Goldilocks zone.
Yes, that dynamic balance is key.
Uh,
But here is where the paper uncovers something truly subtle. Stabilizing the conjecture's reward function is only half the battle.
that's the other half.
Even with a perfect guide evaluating elegance and a responsive conjecture generating relevant targets, the Stanford team discovered that the specific reinforcement learning objective used to train the solver can completely crash the entire self-play ecosystem.
Here's where it gets really interesting.
Right.
Wait, so even if the synthetic data pipeline is flawless, the math used to update the solver's weights can break the conjecturer. How does that work?
It all comes down to policy entropy.
Policy entropy. Break that down for us.
Let's contrast two RL objectives analyzed in the paper. First, we have CSIO, which is a state-of-the-art grouped RL objective.
Okay. Seaside.
In standard LLM reasoning tasks like just solving a static dataset, CSPO is highly regarded for achieving excellent asymptotic validation accuracy.
So it's usually the go-to.
Right. And the alternative they looked at is a modified version of the classic reinforce algorithm, which the authors named reinforce 1/2.
Okay. And when they swapped out reinforce 1/2 and used the state-of-the-art C-sub-PO for the solver, what happened?
So solver's policy entropy collapsed almost immediately.
Entropy collapsed, meaning it stopped exploring.
Exactly. In reinforcement learning, entropy is a measure of the randomness or stochasticity in a model's output distribution. A high entropy policy explores diverse token paths. A low entropy policy becomes highly deterministic.
So it effectively outputs the exact same sequence of tokens every single time for a given prompt. Under C-SISPO, the solver became near deterministic incredibly fast.
Yes.
Let me try to visualize this. It's like a student who has memorized exactly one specific path to solve a type of equation. If the test question looks exactly identical to what they memorized, they get a 100%. But if a single variable is changed, they completely freeze and get a 0%.
That is a perfect analogy.
They've completely lost the messy, exploratory reasoning needed to stumble their way into a 50% score.
Exactly. And because the solver becomes that rigid student, its empirical solve rate on any given batch of rollouts concentrates strictly at either 0 or 1.
It either perfectly recites the proof or it fails uniformly.
Right. There is no intermediate middle ground.
And that is a death sentence for the conjecturer, because R-solve is designed to reward intermediate difficulty. If the solver is only ever scoring 0 or 1, the calculation yields a reward of 0 across the board.
The conjecturer receives no positive reinforcement, the gradients vanish, and it completely stops learning.
It's incredible how interconnected it is.
It is a profound finding about multi-agent dynamics. In asymmetric self-play, The stability of one agent's entropy is the literal lifeblood of the other agent's learning objective. If the solver stops exploring, the conjecturer dies.
So how does reinforce 1/2 solve this entropy collapse?
Reinforce 1/2 functions as a relatively simple log likelihood update, but it introduces one critical mathematical condition. It only applies the gradient update to the solver on problems where the empirical solve rate is 0.5 or less.
Wait, really? So it just actively discards the gradient updates on problems that the solver already finds easy?
Precisely. By discarding updates on problems with a solve rate higher than 50%, it prevents the solver from over-optimizing its policy on easy problems.
Oh, wow.
This mathematically preserves the policy entropy, ensuring the solver remains stochastic enough to generate those messy intermediate solve rates. And as long as the solver produces intermediate solve rates, the conjecturer always has a continuous gradient to follow.
That is brilliant. The choice of RL objective isn't just about maximizing the solver's immediate accuracy. It is fundamentally about maintaining the thermodynamic energy of the environment so the conjecturer has room to operate.
It's all about keeping the system alive.
So with the triad established, the guide functioning, and the entropy rigorously stabilized via reinforce 1/2, what happens when we finally unleash this architecture on large-scale compute?
The results are where the theoretical elegance translates into empirical dominance.
Let's hear the numbers.
The researchers deployed SGS on custom training infrastructure. They utilized up to 64 GPU workers specifically for model generation and 128 CPU workers purely dedicated to running the relentless Lean-4 compiler verifications.
That's a serious rig.
And they let the system run for 6.3 million generations.
And the headline result is truly staggering. By learning how to synthesize its own perfect curriculum, the 7 billion parameter DeepSeek Prover V2 model strictly surpassed the pass at 4 performance of the monstrous 671 billion parameter DeepSeek variant.
Yes. And just for context, pass at 4 means the model is allowed to sample 4 distinct proof attempts for a problem. And it is considered successful if at least one of those attempts compiles perfectly in Lean-4.
Right, which makes sense because search is a big part of math.
Exactly. In formal theorem proving, search and exploration are critical. Surpassing a model nearly 100 times its size is a monumental validation of the SGS architecture.
It really proves that a targeted, self-regulating curriculum beats unstructured scale. But how did it perform on the absolute hardest problems, like the stuff the baselines couldn't touch?
To truly contextualize the magnitude of this leap, we need to examine the D-hard dataset.
D-hard, okay.
This is a highly specific subset of 1,346 problems extracted from D3K. The defining characteristic of D-hard is that the strongest standard RL baseline never solved a single one of these problems.
Not even one.
Not even once. Even after 4 million generations, the baseline performance was a flat 0%.
They were fundamentally out of reach for standard optimization. But under SGS,
the 7 billion parameter model steadily climbed, eventually reaching nearly a 10% cumulative solve rate on these strictly out-of-reach problems.
Unbelievable.
It didn't just learn faster, it genuinely learned how to solve mathematics that its baseline equivalent fundamentally could not access.
And the researchers modeled this mathematically to prove it wasn't just a statistical fluke or a localized spike in performance, right?
Correct. They mapped the performance rigorously. They fit a sigmoidal scaling curve to the cumulative solve rate, modeling the performance as a function of log compute.
Like plotting it out to see where it eventually tops out.
Exactly. By dropping the highly variable early training iterations to get a clean fit, they were able to confidently project the asymptotic solve rates, meaning the theoretical maximum performance, if you could run the compute out to infinity.
And what was the theoretical limit they calculated?
SGS achieved a projected asymptotic solve rate of 67.1%.
That's massive.
To put that in perspective, that is roughly 7% higher than the absolute best standard RL baseline that utilized reinforce 1/2 without the self-guidance mechanism.
Wow.
Furthermore, when they compared SGS directly to STP, which is the closest state-of-the-art Lean-4 self-play baseline in the current literature, SGS demonstrably outperformed it after just 1 million generations, and the gap only widened as compute scaled.
So what does this all mean? Let's pull all these threads together.
Yeah, let's recap.
If you are building or researching these systems, the essential logic here is a paradigm shift. Asymmetric self-play is undeniably the key to pushing LLMs past their pre-training capabilities, unlocking zero-shot logic that static datasets simply cannot reach.
Totally agree.
But brute force compute alone is a trap. It inevitably leads to reward hacking and degeneracy. You absolutely must prevent conjecturer degeneracy by introducing an LLM guide to enforce structural quality and relevance.
The guide is non-negotiable at scale.
And beneath the surface, you have to protect the conjecture's gradient by rigorously managing the solver's entropy, using modified objectives like reinforce 1/2 to keep the system out of deterministic extremes.
If we connect this to the bigger picture, the potential of this architecture extends far beyond formal mathematics.
Where else could this go?
Well, in this specific implementation, the ultimate ground truth reward was a formal lean-for compiler verifying logic. It's a perfect, closed, verifiable system. But the authors propose a fascinating question. What happens when we move this triad into non-verifiable domains?
Like moving from mathematical proofs into the messy reality of the physical world.
Exactly. Imagine applying the SGS triad to embodied AI or advanced robotics. The conjecturer writes a goal, say a complex multi-step navigation task in a physical space.
Okay, I'm following.
A neural world model, something akin to DeepMind's Genie, acts as the environment, simulating the physical physics and constraints of the space.
So that's the sandbox.
Right. The solver is the robot's actual control policy, attempting to navigate the simulation. And finally, a vision language model acts as the guide, evaluating whether the generated task is actually relevant to real-world physics and elegantly structured for learning.
That is a wild trajectory. If language models can utilize their latent understanding of elegance to autonomously guide their own curriculum in pure mathematics, they might soon write the curriculum for navigating the physical world.
It's a very real possibility.
They are no longer just absorbing human data, they are actively learning how to optimally teach themselves.
Precisely. We are moving from static knowledge retrieval into an era of dynamic, self-regulating engines of discovery.
And that is where the real scaling laws of the future will be written. Thank you for joining us on this deep dive into the architecture of self-guided self-play. We invite you to ponder how you might apply self-guided data synthesis in your own machine learning pipelines and what invisible bottlenecks you might break by simply letting your models guide themselves.